to restart if we want to be on time for the free drink. It's an opportunity that should not be missed. So sorry for this second lecture today. I'm tired. They walked me in the woods, so I'm totally dead, but I will try to go through the lecture. So if you remember well, we were in the process of quantizing the field. We went up with this idea of separating what is actual space. I had discussion at lunch on that. Perhaps it was not entirely clear. I would say the real physical space in which the limiting conditions live, in which the modes, which are solution of Maxwell's equation, live, and the Hilbert space, which pertain to each mode, in which we inject the photons, which are the field quanta. And we have decided, we have gone through the Fock states, and we have said that they were not very useful, of course, but not physically satisfying, because very far from what we imagine a classical field should be. And we produce the current state, which are those displaced vacuum operators. And we have this beautiful picture that Philippe kindly used again in his lecture, of small quantum fluctuations on top of a classical amplitude. And the larger the classical amplitude, the better the classicality of the field is. So these are good states. What can we say about them? We have shown that they are right eigenstates of the annihilation operator. And this can be taken as an alternative definition of the current states. And it's a good exercise. You can rework from that the displacement operator. What is the unitary that creates those states? You will find that it's d alpha, which means that the field operator has non-zero eigenvalues in the current state. So what the field that Philippe has written in his lecture is basically a laser state coherent field living in a plane wave, or kind of plane wave, which has a classical amplitude. Our phase convention can differ a little bit, but okay, no problem with that. What can we say more? What is the average photon number in a current state? This is easy to compute because alpha is the left eigenstate, right eigenstate of R. So this is alpha, this is the complex conjugate, it's alpha star. The mean photon number is the square of the amplitude. It's a good way to measure the amplitude. It's a square root of photon number. It's clearly a good unit to measure the field amplitude. You can also compute the photon number variance. For that, you need to compute the average of n square. And n square is A dagger A dagger A. And following the general prescription, you can commute the two here to put it in normal order. So we find that it's A dagger square, A square, plus A dagger A. And if you inject that, sandwich that between two current states, using the fact that eigenstates are eigenvectors of A, you will find that n square is alpha to the fourth plus alpha to the 2. And so you will find that the variance of the photon number is just alpha square. It's the average of the photon number. And we know, of course, of one probability distribution whose variance is equal to the average. It's the Poisson law. So we guess that the photon number distribution could be a Poissonian law. More importantly, it says that the relative variance, that is the variance divided by the mean, is 1 over square root n. And that we can understand. The higher the field, the variance of the photon number is the difference between the squares of these lengths, and the higher the field, the less is this difference in relative values. You can say also that there is a phase uncertainty in the current state, delta phi, and the larger the state, the lower the phase uncertainty. And you can even write something beautiful. Delta n equals delta phi is of the order of 1. Of course, what is hidden there is that there is no properly defined phase operator in electrodynamics. For one reason, the phase operator is a state with a perfectly defined phase, so it's infinitely narrow. And since you have delta x, delta p equal 1, it should be infinitely long in the other direction. It has a non-normalizable energy. It's a non-properly defined state. But okay, this is it. And that confirms that the larger the photon number, the more negligible the fluctuations are in relative value. So we can confirm that by finding the expansion of the current state on the Fock state basis. The Fock state is the basis of Hilbert space, so we can expand certainly alpha on that. How do we do that? We rewrite d of alpha using the Glauber relation, like that. Instead of a sum, we have a product of the exponential of the sum, we have a product of the exponentials, and a factor. It works because A dagger A, the commutator, is 1, and that commutes with the operator. If you apply that to 0, if you expand that, that is 1 plus a series of A, and A acting on 0 is 0. So what remains is 1. So alpha is just that. You expand this in power series. So we find a power series of A dagger. A dagger 0 is 1. A dagger square 0 is 2. And so on and so forth. So you directly get alpha as an expansion on n with a coefficient Cn being a normalization factor, alpha to Vn over square root factorial n. It's a very simple expression of the components of a current state on the Fock states. From that, you get the photon number distribution by squaring it, and you get a Poisson law with the average and mean, as expected. And for very large photon numbers, this Poisson law is kind of a Gaussian centered at n mean with a variance n. You can also work out the scalar product of current states. I say to you there are many more current states than Fock states, just because they depend upon a continuous variable. So you might expect that they are not orthogonal. In fact, they are not. The scalar product is always non-zero. Always. And if you work out, it's a simple exercise in maths using the orthogonality, you find that the scalar product is that expression. That's not very talkative in itself, but if you take the modulus square of the scalar product, it's just e to the minus modulus alpha minus beta squared. It means that, of course, if alpha equal beta, the scalar product is 1, normalized state. If alpha minus beta is of the order of unity, the scalar product is lower than 1, but noticeable. If alpha minus beta is of the order of a couple of units, the scalar product is weak, very weak, exponentially so, but never exactly 0. Of course, an experimental's point of view is that a scalar product that is 10 to the minus 10 is FAPP 0. FAPP for all practical purposes. Okay. But okay. Another indication of that, I won't demonstrate that, it's in the detailed notes that you can find on the web. The current state are an overcomplete basis of Hilbert space. Meaning that you can expand any state on the basis of a current state, but this expansion is not unique. Because there are too many current states, basically, to make a good basis. How do they evolve in time? We are in the Schrödinger picture. The operators are independent of time, but the states do depend on time. What is the evolution of that? As a function of time. I just have to put that n is an eigenstate of the energy. So it just evolves with a phase factor, a Bohr frequency, that is the energy divided by h bar. Yep?
Is there just a complete basis which is not ever complete, that you can extract and that people use, that you can extract from the...
Well, depending upon what you want to do, you can find, approximate bases that are to some extent complete. For instance, the Fock state n can unambiguously be written as the sum of n current state of a circle of radius square root n with the proper phases. Within an approximation that is exponentially good when n goes to infinity. Okay, so you can do such things, yeah. But it depends on what you have to do. It's just like mathematically, it's not a proper basis. But okay, if you have a state that is kind of an elongated blob in phase space, you put 3 current states on it and it will be okay. More on that in a moment.
One thing about the slides before this one. So we have like n
Yeah, this is,
expectation value.
yeah, this is the mean.
And what's the normal end then? Does it
Oh, sorry, there is a big mistake here. No, it's n mean to the n, yeah?
because then what's the n, the normal one? Like the exact value of epsilon?
No. I have a p of n. I'm sorry, this is the photon number distribution. It's the probability for having n photons in the field.
Okay.
This probability has a mean value that is n mean. I'm sorry, I went perhaps a bit too fast on that. And the probability for having n photons is, within the normalization here, n mean to the n divided by factorial n. So n goes from 0 to infinity, and n mean is given.
Okay, yeah.
Okay?
That was the,
For instance, if you plot the P of n for a one photon current state, for the vacuum it's easy, just 0. For one photon current state, it will look like that. Okay? Two equal values for 0 and 1, and goes down. If you go for a very high current state, it goes like, basically, what I have written here, a Gaussian. From there to there, you need to use the Stirling formula. Factorial n is n to the n, square root of 2 pi n, e to the minus n, e to the minus 1/12 of n, something like that. I knew it by heart when I was young. Okay, never mind. That's okay? Okay. So n is just, well, okay, the notations, I have too many n's. I have a big N, I have a small n, I have an n in the Fock state, I have the n with another line on it. There are too many n's, but I got a cheap supply of n's on my computer. I just use them too much. Okay. Okay? No other questions? So let's look at the amplitude. So I just have to write how n evolves with time. And n evolves with time at e to the minus en t over h bar, Bohr frequency. I put everything in it, and I see that I can extract the e to the minus I omega t over 2, which comes from a vacuum energy out of that. This is just a phase factor, not very important. And I recognize here alpha to the n e to the eni omega t. And this is just the expansion of the current state alpha e to the minus I omega t with time. So basically, if I have a current state alpha at time 0, at time t I have that state. What does it mean? Is that the current state remains coherent forever, but the amplitude evolves, rotating around the origin at the frequency omega of the mode. This is exactly the evolution that you expect for the classical field amplitude of a mode. Alpha is just the classical field amplitude, evolves as the classical field amplitude. It has everything of a classical field amplitude. Okay? How do you produce coherent states? I don't want to make the whole calculation. Once again, you can find it in the notes. The calculation takes 5 slides, and I don't think it's useful to get through. Basically, by coupling a classical current to the field. If you imagine that somewhere in the space, you have a classical current J evolving at the frequency omega naught, and if you write that the field current couples to the field by an Hamiltonian that is J dot R, because that's just the quantum version of a classical electrodynamics result, the power given to the field is J dot R. If you just write that, and if you write the evolution, you find that what is created in one mode of the field, one mode L of a field, results from the action of a displacement operator onto the initial vacuum state. So classical current, let's forget about the details. A classical current creates a current field state. So what is in the power plugs here is a current state at 50 Hertz. Because that's classical, very classical currents that create that in the big power plants of EDF. What's going out of that is a current state, because inside that I have many atoms that are put into phase by a laser cavity, and which create an equivalent classical current. It's a displacement current, so dP over dt, but yet it's a macroscopic current, and it creates a current state. what gets out of a microwave synthesizer is a current state, because in the microwave synthesizer, you have classical currents. What gets out of that is a current state. Well modulated, because it contains messages. But basically, it's that. So not only they are important because they are classical, but they are also the states that are easier to generate. Okay. And well, if you are at resonance, you see that the amplitude is linear versus time. So there is an interesting fact. If you are at resonance, so if the mode you excite is exactly at the frequency of the current, you find that the amplitude of the current state is a linear function of time, which means that the photon number is a quadratic function of time. So the more field you have, the more field you get. It's a kind of avalanche process, but it's just the bosonic amplification. The more bosons you have, the easier it is to put one more inside. Basically what we discussed this morning about BEC. And basically it's that A dagger as a matrix element that is square root of n. So the more n's, the more easy it is to make A dagger act on the field to create photons. Okay, now I would like to switch gears a little bit and address the problem of phase space distributions. We have plotted these beautiful things, a blob in phase space. Can we go a bit further? Can we apply such drawings to arbitrary states of a field? Can we plot how Fock states look like in phase space? A large Fock state, not the vacuum. Vacuum is trivial. That's not easy. And of course, what we would like to create is recreate what statistical physics does all the time. You have a phase space for your system, and you can write a distribution in phase space, an f of x and p, from which you can compute the average of any pertinent operator. And all of stat phys is based on that, basically. So can we do something like that? Of course, the difficulty is that in statistical physics, x and p are commuting, and no x and p are non-commuting observables. So we should take care of that. And in fact, what can be shown, it's done in all the standard textbook of quantum optics, particularly in the textbook by Wolfgang Schleich, Quantum Optics in Phase Space, you can define as many representations as you wish. There are infinitely many such phase representations. Infinitely many, this is a lot. And infinitely, it's a power of continuum. So I will just get the two simplest ones, the ones that are really useful in everyday life. The first is called the UZMQ representation. And it's sometimes proposed in very, very abstract terms, but in fact it boils down to be very simple. I have a field described by the density matrix ρ. I will stick to using ρ for the density matrix and fighting Philippe, who uses sigma. But sigma is for the two-level atom, ρ is for the field. I will define a function depending upon an amplitude alpha. I want to explore phase space, so I need to give a function of an amplitude alpha, of a complex amplitude alpha, which should be basically the trace of ρ projector on the current state alpha, which you can also write cyclic invariance and orthogonality of the current state, like 1 over p, the average value of ρ in the state alpha. That you can also write using the fact that alpha is a displaced vacuum as the trace of a projector onto the vacuum state in the density matrix, which has been displaced by an amplitude d of alpha, by an amplitude alpha. So you see many, many things. Basically what it tells in everyday life is you have a complex space, a complex state spread in phase space, and you take the overlap of that state with a current state located in alpha. And you promenade alpha in phase space, and like that you sample how your state is made. Okay? What can we say of a Q distribution? It's positive, clear here. It's bounded by 1 over pi. It's normalized, meaning that the integral of the whole space is 1. This is good. It looks very much like a standard probability distribution, positive, integrable, beautiful. Let's look at it for a few states. A current state beta, it's an easy exercise in optics because you just have a scalar product there. It's just a Gaussian centered on beta. Okay, this is a more pictorial representation of this blob. This blob here is just a cut of a Gaussian at 1 over e. Or 1 over e squared, you should think of it. A Fock state, well, it's complicated. Let's look at an interesting state, the famous, or infamous, Schrödinger cat state. What is a Schrödinger cat state? It's a metaphor for the famous Schrödinger cat, which is half dead, half alive in a quantum superposition. It's a current state beta superposed with a current state minus beta. So it's a field which at the same time has a positive phase and a pi phase. It's something that you cannot imagine what it gives when plugged on a scope, very clearly. It's a beautiful example of a mesoscopic field state superposition. If you plot Q, you get that. So, okay, we understand nothing. Let's look at the Q function. This is the Q of a current state. It's a Gaussian. It's a bit wide because I sample my current state, which is a width 1, with another disk that has a width 1. So together they have a width square root of 2, something like that. But it's positive. It's what I imagine for a current state. This is for a Fock state, very much what I imagine too. It's a ridge in phase space. A Fock state, because it has no electric field, has no phase. A Fock state has no phase information in it. So it should be rotation invariant, but it has an energy. It has an energy because if I compute an average amplitude modulus, it's kind of the top of S range. This is the Schrödinger cat state. You have two superposed amplitude, and if you look very, very, very carefully, here you have a little bit of wingling thing, which traces back to this awful expression. And if instead of that, you plot a statistical mixture of either this field or this field, not the superposition, just either or, 50% probability this field, 50%, you will see that this little wiggling here goes away. So it's fine, it has all the virtues, but here you have a totally classical field. You have either a current or the other. I've prepared either of them, but I don't tell you which. So the state you get is that. Here I have something entirely different. I have a quantum superposition of states. And the difference is basically impossible to see. Q is too smooth. Why is Q too smooth? Because you have used a current state that has a width 1 to prove the phase space. It's not good. It's too coarse. It's a misty view of a phase space. Can we get something better? Of course, when you ask such a question in a seminar, the answer is always yes. I've never seen that. Can we get something better? No. Quit it. Okay, can we get something better? Yes, we can. We can define the Wigner function. There is a very sophisticated, elaborate definition of a Wigner function in terms of non-diagonal Fourier transform of non-diagonal elements of a density matrix. Awful. There is a much simpler one. W is the average of some parity operator in the state after it has been displaced by an amplitude minus alpha. What is the operator here? It's called the parity operator. And you know all of it. It's the same parity operator that you have in atomic or molecular physics. P of x is minus x. P of p is minus p. Hence, P of n is minus 1 to the n, n. Because the wave function of the n photon state is a parity minus 1 to the n. In other words, P is nothing but e to the I pi a dagger r, a. I pi number of photons. So it takes the photon number as eigenstates with an eigenvalue plus 1 for even photon numbers and eigenvalue minus 1 for odd photon numbers. So it's a very simple operator, and it turns out that it's measurable. It's a Hermitian operator. And you will see later in the cavity QED lectures how we can design a measurement direct of this operator. In other words, the Wigner function, you can measure it. Displace and measure the parity operator. That's all you need. Since the modulus of P is lower than 1, you get that W is between minus 2 over pi and 2 over pi. But it can be negative, because the parity is negative. If you take the one photon Fock state, its parity is -1. So W can be negative. Hence, it's not a proper probability distribution. Okay, but that's neat, because we will see everything we want. There is a very important property that is unique to the Wigner function. Is that the probability for the x quadrature, x is also called the quadrature, probability for the x quadrature is just the integral of the W over P, and reciprocal. So the marginals, it's called the marginals of W are the probability distributions. It's a way by which you can measure the Wigner function also through state tomography. So let's look at the W's. W at the vacuum. Beautiful Gaussian, you may observe the scalar about the same, but it's much narrower than Q. Q is smoothened out. W is sharper. W for a current state is also a sharp Gaussian. This is perfect. This is W for a thermal state. It's a blob. A thermal state is a mixture of currents of Fock states, so the W function is a blob, Gaussian. This is the W of a squeeze state, which is often called as being a non-classical state, and that you get by acting this operator on a current state. It has fluctuations in one direction of phase space that are lower than fluctuations in the other direction. And it's useful for quantum metrology. But it's still a Gaussian, it's still positive. If I think of all those states in terms of a probability distribution, it's a standard probability distribution. It's positive, and I can understand all of those states just as a classical amplitude that is fluctuating with fluctuations given by this probability law. And I can understand most of the probability of these states, even the squeeze state, which is really classical in fact, in very classical terms of fluctuating amplitudes. And by the way, every state which has a positive Wigner function, the Wigner function is a Gaussian. There's a beautiful math theorem on that. But now let's look at more exciting states. This is a 5-photon Wigner function. You see, it's entirely different from the Q function. It has negativities. It has a big dip inside, and it goes all the way down to the minimum allowed value -2 over pi. It means that if you think in terms of fluctuating field, in a 5-photon Fock state, the probability for having a zero amplitude is minus something. It's not a probability distribution, but it's the price you have to pay to get a faithful description of a quantum field in spite of the limits due to the Heisenberg uncertainty relations. And you see wiggles here, 5 wiggles. You recover that there is no phase information. W is rotation invariant. But certainly you have more information in that than the mere ridge of the Q function. And the cat. To-doom! You have what is required in a cat. You have 2 ears. That says to you there are 2 current fields in that. But in between the ears, what do you have? You have a smile. It's a Cheshire cat. You have a smile, and the smile are huge interference fringes with big negativities and big positivities, which tell you, Jesus, what you have here is not a current mixture of this, is not a statistical mixture of this, it's indeed a current superposition. The little wiggles that we barely saw in the Q function have been exponentially amplified by going to the Wigner function and result in these huge interference features. So, and if you plot a statistical mixture, I have not it here, but you just have the 2 Gaussian blobs. Nothing in between. So the Wigner function, I like it very much. First, because it can be negative. And if you see negativities in the Wigner function, it tells you that there is no physical explanation to your state. You cannot get a clear statistical picture because you would have negative probabilities for the amplitude. There's not randomly choosing a thin amplitude. It's something entirely different. And these interferences are a very visual recognition of a non-classical nature. Whenever W goes negative, you know that your state has something in it that is utterly non-classical. If W is positive, you just have boring classical states. Okay? So it's a clear-cut test added to the fact, of course, of the machine. So you have in the notes all the expressions. Well, okay, the expressions are complicated, but nothing that unbearably so complicated. And for instance, this one, if you want to get through exercises on Sunday to enjoy your lunchbox, you can rework that out. It's not very difficult using all what I have told you. It should fit. Okay? Nice for that? So we use that extensively in QED to understand the classical physics. So in the last part of this chapter, I think I can address next chapter in the end of the lecture. But in the last part of this chapter, and we'll go back to what Philip was, yep?
Why would I use the UCMEQ distribution?
The UCMEQ, it has the merit of being positive, so it's easier to plot. It being smooth, and it's being easy to measure. To measure the Wigner function, this is an excellent question, by the way. To measure the Wigner function, you need to measure the parity operator. And this is a somewhat complex operator. It means basically that you have to measure, for a state, the parity operator is, the average is sum of P of n minus 1 to the n. So you have to measure the photon number distribution. And not that easy. Whereas for the Q function, you just need to measure the projector on the vacuum state. I take my state, I displace it by the amplitude alpha. What is the probability for having the vacuum? This is much easier to measure. Just measure one state. Okay? So this one is easier to measure, technically. Wigner is a bit more difficult. I should say that it's a highly constrained mathematical function. Due to the positivity of rho, you have many constraints of W. And so you can also reconstruct W by using max-like estimates. There are many ways to if you don't want to measure at any point, measuring a couple of well-chosen points is enough to reconstruct the general aspect of W. Okay? That's it? So once again, these are trivial exercises in quantum optics. Well, trivial can take a bit of time. And I encourage you to go through, if you are interested, of course, to go through these exercises. Now I would like to switch gears completely and address the general problem of quantum relaxation. What is it to introduce dissipation in a quantum system? For the time being, I only had a quantum system. It was in the Schrödinger picture, in the Heisenberg picture, in an interaction picture. But okay, states, energy was conserved. Everything was neat and clear. What if I put dissipation? What I have in mind here, for instance, if we consider a field, is obviously the case of a cavity field. If you have a cavity, an optical cavity, you have a standing wave between the mirrors, standing wave mode, but part of the radiation is leaking out. So if I put energy on the cavity, the energy will eventually decay away. How so? How does a Fock state decay? How does a current state decay? Do they remain Fock state? Do they remain current states? We have to address that. What I could consider also is a propagating laser beam through a medium. Some photons will be scattered out. If there were mist, or when there will be rain tonight, you will see that the light is scattered. What remains of the beam out? I put a current state here. What remains here? What remains if I send a current beam across a series of beam splitters that take away part of the energy? What remains in the current beam? What goes in the beam splitter ports? So all that are problems of relaxation, but are just examples of a much wider problem. I have a quantum system S, and I let it interact with a big environment, big, large, beautiful E. What happens to the quantum system itself? How can I describe the evolution? What is an environment? A large chunk of anything. The whole modes of the vacuum radiation field. There are many such modes. It can be, I don't know, a big reservoir made of atoms, made of solid, a big chunk of matter, generally. It can have a finite temperature. Well, ideally, it can be at 0 temperature. It's a big chunk of the thing, so big, basically, that it's impervious to the interaction with the system. When an atom emits in the continuum of modes in the universe, the continuum of modes doesn't care too much. Okay? When an atom excited hits the wall of a room, it most probably releases a 1 eV energy, but I would say that it will not cause, at short term, the destruction of the walls in the room. So the walls are a good environment. It doesn't care of what happens to the system. That's the key to that. So the idea is we have a quantum system, we have environment, they are coupled together. You need to get a model for the coupling. And what you want is what happens to the system alone. Because the environment is something so complex, the information is just lost in it. The famous fantasy of recording Bach playing the harpsichord from the actual motion of the environment of the air particles now, which keeps track, of course, in the initial condition of Bach playing the harpsichord. There is no way to retrieve that information, classically, or even more importantly, quantum mechanically. So how can we treat that? So what we want is write the state of the system plus environment, because system, the environment is the whole universe. So system plus environment is a closed system, and we want to get an equation which only describes the density matrix of the system alone. It will be a density matrix, of course. And that can be done in a variety of ways. If you look at Steve Barnett's mathematical methods in quantum optics, you will write how to make a model of the environment, to write a linear coupling between the model of the environment, to make the Born approximation. Basically, whatever goes in the environment is lost forever. And the Markov approximation, basically, the environment has 0 memory, because it's so big, so large, that all its observables are shaking like crazy. You do that, you turn the crank, you write a second-order perturbation, you return the crank for 20, 25 pages of dense calculation, and you get at the end an equation for OS. But is model dependent, to some extent. There is a much simpler approach, very much inspired by the famous Preskill quantum information lectures. I urge you to read Preskill's lecture notes, which are on the web, free access, which is based on the idea of quantum maps and cross operators. So I would like to enter in it because it's not only important for this course, but it's also important for spontaneous emission. It's important for any quantum relaxation. And basically, you can phrase any quantum relaxation process in those terms. And you will see that it gives a very intuitive picture of relaxation. Basically, I'm an experimenter. I want to know how my system evolves. But I don't care to know what is the exact form of the coupling of that mode with that mode of the environment. I just want to write an equation and to have in the equation some experimental parameters that I could fit. Experimenters usually fit. But I could fit on an experiment that I could do. And that's precisely what the cross approach will teach out to do. So I will do it very, 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 very fast. Decently fast. I will skip many mathematical details. I will make many hidden mathematical assumptions. I've seen that done properly once by a good theoretician. It takes 3 hours. I will try to do that in less than a quarter of an hour, which means that I will skip many mathematical details. So I don't pretend here to have any mathematical rigor. But at the end, if you do it with all the maths, you get the same result. So why bothering with all the maths if you can get the same results without the maths? Okay? Experimental. Yeah.
Can you repeat the approximations which we use here when we consider system reservoir input?
The only thing I will require, I will go on that later. I don't require that many things. The only thing I want is the reservoir to be big, really big, meaning large, enormous energy, meaning many degrees of freedom, evolving at many frequencies, basically all possible frequencies you can imagine, from 0 to mc squared, where m is the mass of a room. That's the definition of an environment form. Once again, it's a definition that would need to be put in proper terms. There are very great subtleties, particularly in the Markov approximation. And if you go to people who are studying non-Markovian terms, they will tell you that my view is a completely simplistic view of a stubborn experimenter. But it can be given in 15 minutes, perhaps 20. Okay? So, what I want, I drop the index S because I have always the system. What I want is to know how the density matrix of the system evolves. Rho. And if I take it at time t and at a time t plus tau, where tau is small enough so that I will be able to consider derivatives, of course, but large enough, tell a little bit of that. I'm interested in the transformation of rho in rho of t plus tau. Tau, yes, should be much greater, should be small enough so that I will, at the end, be able to write that rho of t plus tau is rho of t plus d rho over dt tau. Okay? But it should be a bit large, nevertheless. I told you the reservoir is immense. It has very, very many frequencies. And you can define a correlation time that is basically the inverse of the difference between the extreme frequencies. It's kind of a memory time of your environment. Tau should be much greater than this correlation time. Just because you get into difficulties if it's not the case. But it's not a problem. If you take spontaneous emission, the correlation time of the environment is what? The optical frequency, 1 over the optical frequency. So, okay, whenever gamma, the spontaneous emission rate that we will define in the next lecture, is much smaller than the optical frequency, it's okay. That approximation would break only for very, very highly dense systems, which decay so fast that they have no frequency in it. Okay, so I forget about that. And so the transformation from rho to rho is a quantum map. It's something that, it's an operator, a super operator, that takes a density matrix and transforms it in another density matrix. A little bit of math, nevertheless. A proper quantum map is a linear operation. L acting on rho 1 plus rho 2 is L acting on rho 1 plus L acting on rho 2. It's a linear operation. It's a super operator in the space of the operators, which has dimension n squared, where n is the dimension of Hilbert space. So it's an n squared by n squared matrix. Okay. As long as I don't have to write it, it's okay. It should preserve a trace. The density matrix, the trace of a density matrix is 1, because it's just normalization of probability distribution. It should remain 1. So it should preserve a trace. It should also preserve a positivity. A density matrix has no negative eigenvalues. The eigenvalues are 0, they can be 0 or positive. So there should not, a quantum map may not have negative eigenvalue because it would mean negative probabilities. And it should be completely positive. Completely positive means if your system S is entangled with S' at time t plus tau, the reduced density matrix of S should be positive. It's not always the case. There are very subtle cases in which that complete positivity is not respected. So if your quantum map checks all these marks, and it should, okay, because the fact that S relaxes is not linked to S being entangled to. If S is entangled with S prime, the relaxation of S should not introduce any negative probabilities. In other words, that's the key. Then it's shown that L can be cast under the form sum over mu, m mu, rho m mu dagger, where the m mu's are called the Krauss operator. They are normalized with this condition, and they are at most n squared, where ns squared, ns is the dimension of Hilbert space, such operators. So all quantum maps can be cast under this form. Okay? This is an important result. It's not absolute. And well, you can show it. It takes a couple of pages, but you can show it. It's not totally intuitive. I should note that the cross operators are not unique. You can change them by mixing them for a unit matrix, and you get exactly the same quantum map. So there are infinitely many representations of a quantum map in terms of cross operators. Okay? Nobody has reactions? That maths. Maths is God-given. What fits in this representation? The Hamiltonian evolution. If you evolve a density matrix with a constant with a Hamiltonian, you just sandwich it between U dagger and U, where U is the evolution operator. And it's directly a cross form. So standard evolution, the map representing the standard Hamiltonian evolution of a system, is directly in a cross form with a single operator, that is the evolution operator. A generalized measurement. Yep.
The cross operators, when you say they're not uniquely defined, it's like a change of basis that you can do, and then you get...
It's a change of basis for the cross operator. Basically, it's a basis to expand the super operator that describes the map. Right, with many quotes. So here you could choose another form with very complex operators replacing U, but there is one form that is natural. A generalized measurement. You know that a generalized measurement is described by a POVM. Okay, I don't want to enter into that, but basically, rho goes into, if you get the result mu, into rho being sandwiched between two operators, O mu, that describe the measurement and its probability, divided by some normalization, which is the square root of the probability for observing this value. Because of the division, it's a highly nonlinear map. The measurement that you read is a highly nonlinear map because of this division by the probability. But if you don't read the result, you make the measurement and you don't read the result. The state after the measurement is the sum of all possible results of the probability of a measurement times the density matrix resulting in the measurement. So it just reduces to that. An unread measurement is a cross form. Okay, so this is the read measurement. Okay, so it seems to fit. So let's go. Rho of t plus tau, the new density matrix of a state, can be certainly cast under this form with cross operators. But if tau is properly chosen, this is also rho of tau, t plus d rho over dt tau. So d rho over dt can be cast in terms of Vm mu's. Let's go into that a bit more. What about Vm mu's? They, of course, depend on what the environment is doing to the system. But as the environment is very, very large, it's in a steady state that is not affected by the system. Once again, the walls in this room are not affected when they absorb a single photon. So Vm mu's should not depend upon time t. They only depend upon the time interval tau that is there, because it's the map from rho of t to rho of t plus 2. They depend upon tau. Of course, the trace of that is 1. The trace of that should be of the order of 1, which means that in terms of the small variable tau, at least one of Vm mu's should be of order 0. There should be one of Vm mu's that is of the order of V unity. If all are proportional to the power of tau, then this equation cannot hold. It's where there are many mathematical hidden assumptions. So we call it m naught, and assume that m naught is basically the unity minus a small correction in tau. And I will expand everything to first order in tau. All the others 1 for mu not equal to 0 are what? They only describe the increment of the density matrix, because this one already cares of a constant part. Rho of t plus tau is basically rho of t plus small increments. Small increments proportional to tau. So all the m mu's that are not m naught should contribute to this sum by something that is proportional to tau. So the m mu's should be of the order of square root of tau, because there are 2 of them in the sandwich. So if you believe in that, there are many, many hidden maths there. There is one operator that is 1 minus something in tau, which I call ik tau. And all the others are square root of tau, something else that I call L mu. Okay? What about K? K is one operator in the Hilbert space. A very general operator. It need not be Hermitian, unitary, it's anything. But anything can always be divided in a Hermitian part, which is basically K plus K dagger, and an anti-Hermitian part, which is A, K minus K dagger. But whatever. So, M naught is basically 1 minus A tau over H bar H minus G tau. Let's plug. M naught rho, M naught dagger is that. And you see with some satisfaction appearing the term H rho at order 1 in tau, which says that d rho over dt contains a term that is H rho. So it's tempting, fascinatingly tempting, to identify the H, the Hermitian part of the K operator, with the system's Hamiltonian. So I do it, because it's tempting, I do it. Without any mathematical rigor, of course. And this is an anti-commutator, disgusting anti-commutator. But M naught dagger M naught is 1 minus 2 J tau, because in that expression the H part cancels away. Yep?
One question, if you could go back to the slide, because the M0 has 5 proportional to tau, so if I apply that to the rho, I get some term as well that is proportional to tau squared. No?
Yeah, but I will keep the development only to the first order. What I want is to get the equation to first order in tau. To get first order in tau, I have to put square root of tau in all the M mu's that are not M naught. And for M0, I have to put a tau term, because if I take only over 1, I have no tau term. But of course, I will discard any term that is tau square. My computation will be to first order in tau. So I have to take half order for M mu's and first order for M naught. Well, that my development is fully consistent mathematically is certainly an open question. No, it's not open. It's not consistent.
When you say one and only one of the MUs is of order
1.
order 1, is it because there exists a representation, a cross representation?
If I had 2, I could unite them both to make one that is and put some other stuff in the other square root of tau. I guess I could. So I can. Once again, mathematics is not at stake. So if I guess I can, I can. Okay? No, but I tell you, it's 3 hours to do that in proper mathematical terms. I urge you to look into that if you wish. Okay? Okay? So I have cross operators. I have at most n square of them that describe this map. I have cross operators. 1 is order 1, 0 and 1. All the others are order 1/2. And when I use this decomposition of the order 1 in M naught, I get this equation for M rho sandwich between M naught and M naught dagger. Do the calculation for yourself. The only way to understand the calculation is to do it yourself. There is no way by which you can follow all the steps, but you get a commutator, you get an anti-commutator because of the I, which is in J, okay, there are signs, you have to get through it. It's not that difficult. So I'm glad because there I understand something that looks like, this H part looks very much like a Hamiltonian, and this J part is innocuous because M naught dagger M naught is 1 minus 2J2. So J, because of this property, J is just 1/2 the sum over mu not equal to 0 and mu dagger L mu. So J is just something, this anti-Hermitian part of the Hamiltonian, of the M naught operator, is just something that takes care of maintaining normalization, of maintaining trace 1 operator. Basically, the L mu's want to diminish the trace and you have to put the j to raise the trace so that it remains 1. And so the j is known when you know all of the L mu's. So you push, you plug, you put everything back together, you push the L mu's, you don't forget them, you work a little bit, and you get this very beautiful equation that is called the Lindblad equation. d rho over dt is minus a over h bar, h rho. This is the Hamiltonian part of the evolution. H is the Hamiltonian. Cannot be anything else. And you should recover it, of course, because the system may evolve. So H is the Hamiltonian of the system alone, without environment. Plus the sum over all mu's, the L mu rho, L mu dagger, minus two terms, L mu dagger, L mu rho, and rho, L mu dagger. But those terms are basically originating from the J part. Those terms here are just to keep the normalization, trace 1 operator. The key term is this one. Okay? The striking thing is that if you do the Barnett way, if you assume a model, if you compute the model, if you turn the crank for 25 pages of second-order perturbation theory on the model, you get this equation. Or an equation that can be cast under this form. The only thing is that since you have an explicit model, you have the expressions of the L mu's. But it can be cast under this form. But if I don't want to do the whole calculation, the only thing I have to guess what happens to rho is to get what the L mu's are.
Is there a constraint in the L?
No constraint whatsoever. They are order 0 in square root of tau because they factor out the square root of tau. There is no constraint. The constraint is about the physics. Let's look at that. Let's forget about the normalization terms. Okay, we can work for a while with non-normalized density matrices. Well, by the way, when you code the thing, you work with non-normalized density matrices and you normalize later. And let's assume at time 0 that I have a pure state psi. And let's write the state at time tau based on the Lindblad equation. So I get rid also, I can use an interaction representation to get rid of h. So the only term that remains is that term. And what I get is that rho of tau is the initial state, psi psi, plus a term proportional to tau that is the derivative. And the derivative, it's easy. It's L mu rho, L mu dagger. And if I expand, it's L mu psi times psi L mu square, L mu dagger. Look at that. Look at that in terms of a density matrix. What I'm saying there is that if I'm in the pure state psi at time 0, at time tau, I'm with a probability of order 1 in the same state. Okay, relaxation is slow compared to tau. That was the initial assumption. But with a probability of the order of tau, I might have done the transition to a state L mu psi. Okay? So either my state remained constant, or it jumped to a state that is L mu psi. So during the time interval tau, you have to understand that. It's very essential point. All the rest is fake maths. Not fake news, but fake maths. In the small time interval tau, either nothing happens, which is of course extremely likely, if tau is short enough, or if something happens, it's just the action of one of the L mu's operator onto the state. So either the state is constant or jumps to something that might be totally different because the L mu's have no constraint. They are operators of order 1. All their matrix elements are of order 1. The state can jump with a small probability to something entirely different. It's why the L mu's are called jump operators. Because the state, if the L mu acts, jumps. They walk me in the woods, so I have difficulties in jumping now. But can jump from psi to L mu psi with a small probability. And so the intuitive picture that we get out of that is nothing happens most of the time, but sometimes something dramatic happens. Take an atom emitting in free space, the gamma of Philippe a moment ago. My atom is in excited state at time 0. At time tau, what it says is that it can remain in the excited state or something could have happened. But what can happen to an atom which has only 2 levels? What jump can it make? It can jump to the other level. There's not much more than you can think of. So you see that a relaxation of an atom should be described by a single jump operator, L mu, that is the S minus of Philip, the adjoint of S plus, that is the downward going jump operator. And you might have a factor that accounts for the probability of this to occur, and this factor would be square root of gamma. So you intuit for immediately that for a 2-level atom, the jump operator is square root of gamma S minus. So you see the strength of that is that you need not work out a standard model of what happens. You need not to work out an environment model. You need not this huge machinery of second-order perturbation theory. You just need, looking at your system and getting the physical insight of it, guess what can happen when it relaxes. When a field relaxes, what can happen to a field that relaxes? The only decent thing it can do, you should not personalize the field, the only thing it can do is lose a photon. I'm ready to bet my left leg that the only jump operator is A, the annihilation operator, with some coefficient. But the coefficient, I can fit it on experiments later. So you see, it's an extremely economical insight into relaxation. You just need to guess what can happen to your system when it jumps. And then you have the operator that makes the jump. You have the Lindblad form within some coefficients that you can fit to the experiment. The gamma, the spontaneous emission lifetime for the atom, it will be the damping rate of the cavity for a cavity. Did you get it? So it's not mathematically, well, that's unwavering arguments, all that, on the math side. But okay, the mathematician can put that in the real stuff. But you can guess what the evolution is, and once you have guessed it, you just have coefficients to measure, to make sure that you understand your relaxation. It's very powerful and very intuitive picture. Of course, there are caveats. The M mu's are not uniquely defined. So the L mu's are not uniquely defined. You can shuttle them in a unitary transform. So it means that the jump operator is not uniquely defined. Instead of A, you could take A minus plus alpha and A dagger minus alpha star, and it would work at the end of the day. It would be just, it's called an unraveling of a master equation. And you have infinitely many unraveling of a master equations. But some of them can be useful because they could describe what happens in a specific experiment. For instance, you monitor a decaying atom by looking at the photon either with a photon counter, gets click, and that's the sigma minus, or by homodyning the field with a current source and looking at the difference of the homodyned currents, and it could give you another representation of a jump. But most of the time, you just take the simplest. It works. So you don't need to care with that. And that leads also to something that is numerically super useful, the Monte Carlo approach to relaxation. Frankly, getting to integrate the Lindblad master equation is a pain in the neck, because rho is a dimension which is n squared. So if you have already a spin 1/2, dimension 2, your rho is a 2x2 matrix with leaves in the 4-dimensional space. So you have to integrate 4 differential equations. If you have 1,000 of velocity class in a cold atom sample, then you have to integrate 1,000,000 of equations. Okay, and it becomes very rapidly unpractical. Okay, unless you have a quantum computer, but that's a totally different topic. And I guess you haven't. So this leads to what is called the Monte Carlo method. Of course, in all that, I imagine the jump, I guess the form of the, but at the end I go back to this differential equation. because I don't monitor what the jumps are in an actual situation. I just have to average everything out. But I could imagine I could. For instance, I could see a field decaying by monitoring one by one the photons that go away and getting clicks when a photon goes away. So I know when the jumps occurs. I know exactly when the jump and what jump has occurred. I could imagine that. And if I do the proper averaging, it will give me back the results of a master equation. This is, this is the Monte Carlo algorithm, as you should. You have to think in terms of trajectory. A trajectory is an evolution of a system state, which is a continuous evolution in between the jumps, and from time to time, random jumps, described by one of the jump operators. One given evolution like that is a very bizarre evolution in which the state psi evolves slowly, jumps, evolves slowly, jumps. This is not the actual evolution, and we'll see in experiments the difference between both. But if you average that over all possible histories, you recover the evolution of a density matrix. So how do you do that? You choose initially an eigenstate psi of rho, and for each time interval you evolve psi. You compute p mu here, which is the probability for having the jump mu, and p naught, which is the probability for having no jump at all during the time interval tau. Trust me, the maths work out properly. This is easy. You use a good random number generator, not the one that is supplied with your C compiler or Python compiler. They are devastatingly bad. To decide upon the result of a measure of to decide whether there is a jump, sorry, this is a strata of a previous slide, to decide whether you have a jump, and if you have a jump, what jump has occurred. If you have no jump, you evolve psi with this Hamiltonian, which is the standard Hamiltonian term. The normalization term, you should not forget it, should remain normalized, divided by square root of p naught psi. So this is the evolution of psi if you have no jump. Note that this evolution, so to speak, uses a non-Hermitian Hamiltonian term here. So there is a J term. If the result of a measurement, if the result, there is no measurement, I'm sorry, this is an old slide that I should have rewritten, but taken anyways. If the result is that you should have a jump, then do the jump. Psi is replaced by L mu psi, and you normalize it. So in a time interval, either you evolve a little bit with a non-Hermitian Hamiltonian, or you make the jump. And you go for the next time interval. And you follow psi over time t. And then you do that again for another trajectory. And for many of those trajectories, and at the end you compute the average of the projectors, and it's exactly the solution of the Lindblad equation. That's easy to show. Big advantage. You only have to integrate the evolution of a state vector and not a density matrix. So you go from 1 million to 1,000 equations. It's infinitely simpler. Price to pay, it's true only statistically. One trajectory is not the whole story. If you want rho, you have to average many trajectories. But with, say, 1,000 trajectories, you have a 3% statistical uncertainty of the observables. That's already okay to get a glimpse. So as soon as the Hilbert dimension is larger than, say, 1,000, this method is infinitely superior to the integration of the standard Lindblad equation. This has been proposed in a very seminal paper by Jean Dalibard and Klaus Möllmer shortly after the 1990 Les Houches School. Okay? So the interest is there, it's faster, anyway, and it gives a very clear picture. I will treat in the next lecture, I think, the relaxation of an atom. But let's address now the problem, field relaxation. So I have a cavity that is coupled to an environment, and I will even put it at finite temperature T, just for the fun of it. What can happen to the field? What are the jump operators? Either I can do nothing, of course. I can lose a photon. the jump operator should be something proportional to A, with a constant that should be square root of kappa minus. Kappa minus tau is the probability to lose a photon in a time interval tau. But since I'm at finite temperature, I can also create thermal excitations. So there is also the possibility of jump operator that is I dagger, that creates a photon, with a rate that is square root of kappa plus. But of course, kappa minus and kappa plus are not independent. You should reach a steady state. You should reach a thermal equilibrium at some point. It means that the ratio of kappa plus and kappa minus is just given by the Boltzmann law. Kappa plus is smaller than kappa minus with a factor that is e to the minus the energy of a photon divided by kT. And of course, at 0 temperature, kappa plus is 0. You cannot create excitations from a 0 temperature environment. So if you use the mean number of thermal photons in a mode at temperature T, which is given by the Bose law, there is no mu in that because it's photons. They have no mu. And so NTH is just that. You get this ratio and you get different expressions of that. NTH is just given by the temperature of the environment. So at the NK plus, you know it when you go to no kappa minus. You have one single adjustable variable that you don't know from the model, that is kappa minus. And at the end of the day, this is the Lindblad equation that completely describes the relaxation of a field at a finite temperature. You see how economic it is? I've written no model. I just written what are the jump operators, use a bit of thermodynamics to guess what is the ratio of the jumps up and down. It's Boltzmann law, no big deal. And I get something that is totally finite, in which this is the field. I got rid of a 1 over h bar omega. This is the Hamiltonian of the field. This is the term by which I lose photons. And I can lose photons either spontaneously, kappa, or lose photons in a way that is enhanced by the blackbody fluctuation. So I have an n there. Or I can gain photon in the environment. So observe that A and A dagger are reversed here, with a rate that is proportional to the average number of thermal photons. That's it. It's beautiful. And I have, in all that, there is a single constant, kappa, which depends upon anything else than the temperature of the environment or the frequency of the mode. And this constant, I can measure it. It's just a damping rate. At the end of the day, it's just the classical energy damping rate in my field. So you see that with these arguments, I'm able to write something that boils down to being given by a single constant. And that constant, I don't need to know where the photons are lost in a cavity. I don't need to know whether they are lost in residual ohmic losses, by diffusion, by diffraction, by my finger put in the cavity. I just need to know at which rate they are lost and to measure it. And the details of why they are lost is absolutely not relevant. So you see this Krauss approach encapsulates all the difficulties of a model of environment in a single constant. And, measure it. Don't care. That's beautiful, isn't it? It's okay? You are okay with that? I urge you to go back through the calculations. Yeah.
So now the system is the photon field. And
Yeah.
the environment is
Anything.
anything. Okay.
Anything. For instance, if you take a cavity, the environment is the mirrors themselves, which can absorb the photon, plus if you have defects on the mirrors, the field can be diffracted out. So it's all modes in the universe, plus the mode that is transmitted, plus anything, plus my finger. If I put my finger in the cavity, which is a bad idea, by the way, particularly in a cryogenic cavity.
And also the quantum trajectory basically is just a mathematical approximation for the equation.
The quantum trajectories of that I described in the Monte Carlo method, presented like that, is just a mathematical artifact to compute in a more economic way, what I will show you is that we can indeed measure the field in such a way that you can see the individual trajectories. And that you can see the photons escaping out of a cavity one by one. Which was one of the reasons why in the 2012 Les Ouches Predog School I had to quit abruptly on the 10th of October the room and quit the Hélène Perrin lecture because the Nobel Prize of Haroche was announced. This is beautiful. You will see that on cavity QED chapter. So, interestingly enough, you can boil that to an equation for the P of n, for the photon number distribution, and you just get that P of n is fed by P of n plus 1 by decay, feeds P of n minus 1 by decay, and also can be fed by the others. Yeah?
So the value of this kappa parameter, I can basically measure it in an experiment or fit my model to the experiment.
Yeah. I will show you in a moment what experiment you can fit.
Okay, and I also can look at like how the steady state in the end, for example, changes with kappa.
Yeah. The end thermal I know because I can put a thermometer in the environment to measure its temperature. Or I can look at the steady state thermal field as well. And the kappa, I can measure it by putting a big energy and looking how it decays. In a moment, by putting a current state and looking at how it decays.
So, but it's not fixed in this model.
I cannot compute it from first principles. It's very hard to compute how many photons are lost in a cavity due to a scratch on a mirror. You understand immediately that it's a complex electromagnetism problem. And no fully complex problem. But okay, I don't care. For an experimental point of view, I don't care where the photons go when they are lost.
So all the nasty details are in the value.
The nasty details are embedded in the K, that is a measurable parameter. Okay? That's neat. Putting the nasty in the drawer and closing the drawer is a good operation. Well. Okay, I think if you look at the steady state, you get a Boltzmann distribution. Okay, the steady state is a thermal field. Let's look at the Fock state. How does a Fock state relax? Yeah, I have it. At t equals 0, I start in a Fock state. And I look at a quantum trajectory. If I go one step, the non-Hermitian Hamiltonian, here I can write it simply, it's minus AH bar J. And J, I'm in a zero temperature environment, I get rid of NTH, simpler. J is the Heidegger, it's just the photon number operator. So the non-Hermitian part of the Hamiltonian is just the photon number operator times an imaginary frequency part. An imaginary frequency kappa over 2. Well, okay, it looks usual. An imaginary frequency, it's a damped oscillator. We all know that. So, if I have no jump, this operator acts. But n is obviously an eigenstate of this operator. So within the normalization, nothing happens to n. So if no jump, the Fock state remains a Fock state. What happens if a jump? If a jump, you act A on the Fock state n. You get n minus 1 once renormalized. So if you look at one quantum trajectory starting at from 10 photons, for many steps, nothing happens. You remain with 10 photons. Then in a step, you have a jump. You go to 9. Then nothing happens. You go to 8. And what you get for one trajectory is a staircase that finally ends up with 0 photons. Another trajectory is another staircase with jumps at different times because they are randomly selected and which ends up with 0 photons. If you average all these together, you get a decay of the average energy. Yes?
I have a question which should be relevant. If you say that it's always intuitive to get the operators, but for example, in this case, if I consider an operator which is a squared, which I lose basically 2 photons, do I get the same?
No.
Do I know that I get the same?
If this is an excellent question. There have been many theoretical papers and a few experimental ones on that. as well. If the jump operator is an A square, then the stable states are Schrödinger cats.
Okay,
It's called reservoir engineering, and the idea of reservoir engineering is that by putting a reservoir that is artificial reservoir and tuning the jump operator that it generates, you can generate steady states of your system that are very counterintuitive. If you put a strong relaxation, which is A square jump operator, then you stabilize Schrödinger cats. It's an excellent question. But technically, it's not that easy to show, but okay. And you see, so if you average all that out, you recover an exponential decay of the energy. But of course, you see that initially you have no fluctuation of a photon number. It's always 10. At the end, you have no fluctuation number. It's always 10. But in the meantime, you have a wide distribution of photon numbers. Just because what you have here, you have a ladder of Fock states. Sorry. Your probability starts there. If you have right equations that go down this ladder of states, so in the meantime, you populate a wide distribution of those states. And at the end, everybody ends up in the bottom. So you see pictorially on that also how the P of n evolves. It spreads and gathers back. Okay? So that's for a Fock state. So very clearly, a Fock state doesn't remain a Fock state. How much time, by the way, does it need for a Fock state to quit the initial 10-photon Fock state? How much time does it need to make the first quantum jump? The probability for a quantum jump is obviously proportional to the number of photons. So the time it takes to make the first jump is just the damping time that is there, that is 1 over kappa, divided by the initial photon number, 10. The higher the photon number, the faster you lose the first photon. And the faster you lose the Fock state nature of your state. Because when you lose on the average 1 photon, you don't know if you are in n and minus 1 or n minus 2. So you have totally spread your Fock state over many photon numbers. And that's okay. It's like fishing in a lake. When there are n fish in the lake, it's n times faster to catch one than there is one fish in the lake. If there are people fond of fishing there, they will say it's totally wrong. Indeed it is.
Would it be correct to say that the steady state in this model is Fock again?
The steady state is a Fock state, is the vacuum. I am at 0 temperature, the steady state is the vacuum.
Only in between during the time.
Yeah, okay. If I was at finite temperature, on some trajectories you would see a creation of photons, and at the end the average photon number would be given by the Maxwell distribution. And the asymptote would not be at 0. Okay? So this is not very surprising. But now, look at the current state. How does the current state relax? Either during a time interval there is no jump, or there is a jump. If there is a jump, I act A on the current state alpha. But alpha is an eigenstate of A. So when I destroy a photon in a current state, I don't change the current state. Oh shit, he's crazy. No, I'm right, but it's not evident. When I destroy a photon out of a current state, it remains coherent. I leave you to think of that and give you a simple exercise. Show me that it's impossible to feed all this planet in energy by having a cavity containing 3 photons coherent state and extracting them one by one to infinity. I have 3 photon coherent state, I extract one, I still have 3 photon coherent state. So I can go and I can extract as many coherent states as I wish. So I can solve the planet's energy problem. Why is it that it is not the case? Think of it. After the drink. You need a drink to think of it. So, when there is no jump, there is no evolution. So if there is an evolution, it's only in between jumps. And what occurs in between jumps? This non-Hermitian Hamiltonian. Okay, I have also the rotation at frequency omega, but forget about it. This non-Hermitian Hamiltonian, which puts an imaginary part in the mode frequency. What is an imaginary part in the mode frequency is that beta, instead of turning at constant velocity omega around it, is damped. So a current state evolves in a deterministic way when it relaxes. It remains forever current. It rotates around the origin in phase space, but it does so with an exponentially diminishing amplitude, down to the vacuum state at the end. But at each time it remains coherent, and at which time the evolution is deterministic. Because nothing happens when there are jumps. So jumps which are the random part of the evolution get away, and you just get an effective Hamiltonian evolution with an imaginary frequency. Isn't that surprising? Isn't that puzzling? How comes that? I just give you a hint of that. How comes that the current state is not modified when you extract a photon? It's very much embedded in the Poisson law. The current state is a Poisson probability distribution. And there is a unique feature. To extract a photon out of a current state, you fish in a lake of Fock states. The higher the Fock state you are in, if you imagine that you are in a superposition of Fock state, the higher the Fock state, the more likely it is to get a photon out. So when you extract a photon out of a current state, you do two things. You extract some energy, but at the same time you reinforce the probability for the photon number before the extraction to be larger than the average. And only for the Poisson distribution, these two effects exactly cancel. There is a metaphor of that. You go to the car retailer in Los Gatos. There is only one car retailer, it's Lamborghini. But it's a very wealthy city, Silicon Valley. You go there, you see a guy coming out of the shop with a brand new Lamborghini car. You can state that on the average he's richer than you. Well, I take the average academic. Why is it that? Because he has emitted a lot of money to get his brand new Lamborghini car, but to emit that much of money, he had much more before. You can guess that he's richer than you even after emitting. It's exactly the same thing for a current state. If it has emitted a photon, it was much more likely to have more photons to start with. And so at the end, it's as rich as before. Which doesn't, of course, resolve the other question. How is it that you cannot save the planet by extracting photons one by one out of a free photons coherent state? Think of it. I think it's wise to stop at this point before exhausting you too much. And have a nice drink. It's written in the notes. You have that the extraction probability is proportional to n, and n times Pc of n is Pc of n minus 1. There is well, it's just a probability argument, simple. It shows that the average is... you have the argument in terms of conditional probabilities. I'm sorry I switched it off before, but it's easy enough to show it. That it's unique to the Poisson law, it's a mathematical thing. Okay. It works for the Poisson law. And trust me on that, it's unique to the Poisson law. Yes?
They have freedom of choosing the Lipschitz operator, so they are not unique. It's the same as choosing like an environment model.
If you have an environment model, it tells you what the Lindblad operators are, what the jump operators are. Changing the model changes them in such a way that the Lindblad equation is not fundamentally changed. The solution is not changed. The form of the equation is changed. So it's basically that. Yeah? There is a beautiful chapter in exploring the quantum around that. I get 5 cents per print, so okay. I have no personal interest in recommending it.